In this video, I am going to use the Newton's second law of motion, the conservation of momentum law, and derive the momentum equation in Cartesian coordinate system. So the first thing I need to do, I need to assume a system with controlled volume and controlled surface. Let's assume that this is our system. Let's assume that this is our system. With controlled volume and controlled surface. The conservation of momentum law states that the rate of accumulation of momentum within the system plus the outward flow of momentum from the system will be equal to all forces that are acting on the system. So let's write that down. The rate of accumulation of momentum plus the outward flow of momentum is equal to the summation of all external forces. Now the forces that are acting on a system, they can be divided in two portions, body forces and surface forces. The body forces are those forces due to the gravitational, magnetic, or any sort of electrical effect. And it can be denoted by pound per unit mass or per unit volume. And surface forces are the result of the action of the neighboring fluid mass on the fluid within the volume of our system, like stresses. So this portion, that this is equal to the summation of all external forces, it can be divided in two portions. We can write this as the summation of all body forces plus the summation of all surface forces. So this is the conservation of momentum for the system. Rate of accumulation of momentum within our system plus the outward flow of momentum from our system is equal to the summation of all body forces plus the summation of all surface forces. Now, let's go ahead and translate this statement into a formula. For the first portion, let's assume that we have a differential volume dV within our system. Momentum, by definition, is mass multiplied by the velocity. Momentum is equal to mass multiplied by velocity. Now, right in this situation, since we have motion involved, we got forces involved, let's translate this statement into a formula for one direction. Let's write this formula for x direction. We will write this formula for x direction, then when we get the end result, we can generate a general formula by using the index notation, and then easily we can write the formula for any component that we want. So momentum is equal to mass multiplied by velocity. So accumulation of momentum within that differential volume. So the mass of that differential volume can be shown as rho dV. Mass by definition is density multiplied by the volume. So the mass of that differential volume will be rho dV. So the momentum within that differential volume in x direction will be the mass multiplied by the velocity in x direction. So let's write it like this, rho Vx dV. So this is rho Vx dV is the momentum in x direction in that differential volume. Rate of accumulation, that means partial derivative with respect to time. Now this is the rate of accumulation of momentum within this differential volume. So for the entire volume of our system, we have to take the integration over the entire volume of our system. So this is the first portion of our statement, plus the outward flow of momentum. For this portion, we are going to assume a differential surface, and we show that surface by vector ds and let's assume that the mass is flowing out of that differential volume, the differential surface, with the velocity of v, let's say in this direction. Now, the volume flow rate out of that differential surface, by definition, volume flow rate is equal to the velocity multiplied by the area. So in our case, that we have two vectors, our volume flow rate will be v dot ds. So the mass flow rate will be, by definition, density multiplied by the volume flow rate. So our mass flow rate will be rho v dot ds. Now this is our mass flow rate out of that differential surface. So our momentum in x direction out of that differential surface will be the mass flow rate multiplied by the velocity in x direction from that differential surface. So will be this multiplied by v multiplied by vx. So we can write that as rho vx v dot ds. So this is the outward flow of momentum from that differential surface. So in order for us to find the outward flow of momentum from the entire surface of our system, we have to take the integration over the entire surface of our system. Is equal to summation of all body forces. We said that body forces can be denoted as pound per unit mass, force per unit mass, or force per unit volume. So the unit mass for that differential volume will be rho dV. So the body force within that differential volume, we can show it as rho within that differential volume in x direction. We can write it rho as body force in x direction dV. The body force in x direction multiplied by the mass of that differential volume. So that we can write it as rho F body force in x direction, we should rho F bx dV. Now this is the body force in x direction. This is the total body force in x direction per unit mass in that differential volume. So for the entire volume of our system, we have to take the integration over the entire volume of our system. Plus the summation of all surface forces. We said that the surface forces are the result of the action of the neighboring fluid mass within our system. I'm sorry, I just wanted to make sure it is recording. So for this portion, let's look at we are writing this formula in Cartesian coordinate system. So let's look at this is our x, y, and z axis. So let's look at one let's look at our differential volume again. Let's say that let's look at the x direction. Let's say that this is zxx and this is dx, this is dy, this is dz, and this in here will be, we can use the Taylor series that we have fx plus dx can be written as fx plus partial derivative of fx with respect to x of partial derivative with respect to x dx plus partial square of fx with respect to x squared dx squared divided by 2 factorial, which this is 0. So we can use the Taylor series and write this as partial derivative of we can write this as sigma xx plus partial derivative of sigma xx divided by x dx. So now we are looking at x direction. The forces on x direction, stress on x direction for sigma xx, we can write that as sigma xx plus partial derivative of sigma xx divided with respect to x dx minus sigma xx. This force minus that force. So this will be equal to sigma xx will cancel out, will be partial derivative of sigma xx with respect to x dx. Now, the net surface force for this, the net surface force due to the direct stress will be this multiplied by this area. And this area is dy multiplied by dz. So this is the net surface force resulting from the direct stress, from the neighboring fluid mass acting on a fluid inside our volume. Now, this is for one direction. Now, if we have the Cartesian coordinate system, x, y, z, so if this is sigma yy, and let's say that this is the component of that stress on x direction, so here this will be the component of this will be sigma yx plus the partial derivative of sigma yx with respect to y direction. So these are the component of this stress on x direction. So that would be plus now we want to find the total surface forces in x direction. So this is for the component in x direction, the stress in x direction. For the component of stress in y direction, will be plus, again the same way, we use the Taylor series. We can write this as partial derivative of sigma yx with respect to y multiplied by dy multiplied by this area this time, which is dx multiplied by dz. So this is the net force resulting from the direct stress for the stress in the component of the stress in y direction, the component of it in x direction. And the same manner for this stress in z direction, for the same manner we can, this will be plus the partial derivative of sigma zx with respect to z dz multiplied by this area, which is dx dy, multiplied by this area, which is dx dy. So this term is the total surface forces in x direction. Now let's go ahead and simplify this. Simplify that. If we simplify this, we can write this as partial derivative of sigma xx with respect to x plus partial derivative of sigma yx with respect to y plus partial derivative of sigma zx with respect to z multiplied by dx dy dz. So dx dy dz is in fact our volume, the volume of our differential volume dv. So the total surface forces in x direction will be for this differential volume will be partial derivative of zxx divided by x plus partial derivative of zyx divided by y plus partial derivative of sigma zx divided by z dv. So this is the total surface forces in x direction within that differential volume. So the total surface force in x direction for the entire volume of our system, we can get the integration over the entire volume of our system. Now we have translated that conservation of momentum statement into a formula for a system. Now let's go ahead and simplify this a little bit. We can write this portion as, we can simplify this and write it as rho Okay, let's before that, let's see. Now we got a we got an equation with 4 integrals. One of the integrals are surface integral, the other 3 are volume integral. So in order for us to solve this, we can again use the Gauss Divergence Theorem and change this surface integral into a volume integral. So this surface integral, we know that the Gauss Divergence Theorem says that if we have a surface integral of a vector A dot ds, this can be written as the volume integral, as a volume integral of del dot A dv. So we can use the Gauss Divergence Theorem and we can write this portion of our equation to the volume integral of del dot rho vx v dv. So by using this Gauss Divergence Theorem, we can transfer this integral into a volume integral. So we can transfer this into del dot rho vx v dv. Now all our 4 integrals are volume integrals, so we can solve this equation. So to solve this equation, let's go ahead and rewrite this equation as control volume of partial derivative with respect to time rho vx plus del dot rho vx v. Let's bring those to the left side, minus rho forces, body forces in x direction, minus partial derivative of zxx with respect to x, plus partial derivative of zyx with respect to y, plus partial derivative of sigma zx with respect to z equal to dv equal to 0. So we just simplified this, brought everything to the left side, and wrote the equation like this. Now, in order for us to reach here, we had assumed a system with a controlled surface and controlled volume. And because of that, this integral cannot be equal to 0. So in order for this equation to be 0, this portion of equation must be equal to 0. This portion. This must be equal to 0. So, in order for this to be equal to 0, partial derivative with respect to time rho vx plus del dot rho vx v. Let's again write it in a first like this. We send this to the other side of the equation, equal to rho force, body force in x direction, plus partial derivative of sigma yx with respect to y direction plus partial derivative of sigma zx with respect to z. Okay. Now here we can simplify this again and write this as rho partial derivative with respect to time Vx plus del dot Vx V equal to that. So we simplified the left side like this and the right side stayed the same. Now after we do the dot product here, we can write this as rho partial derivative with respect to time of Vx plus Vx partial derivative of Vx with respect to x plus Vy partial derivative of Vx with respect to y plus Vz partial derivative of Vx with respect to z is equal to this the right side again. Now here in most books you will see that if you look at the engineering manuals, this operator d over dt is defined as partial derivative with respect to time plus Vx partial derivative with respect to x plus Vy partial derivative with respect to y plus Vz partial derivative with respect to z. So by using this operator, we can rewrite this portion as this is they are using this a lot. If you look at the engineering manual, you see that operator. So by using this operator, we can write this portion as rho dvx dt is equal to the right side, equal to rho forces, body forces in x direction plus partial derivative of zxx with respect to x plus partial derivative of zyx with respect to y plus partial derivative of sigma zx with respect to z. So this is our momentum equation for x direction. Now we can use the index notation and write this equation in a general form. That using that general form, we will be able to write this equation for any component that we want. So we can use the index notation and write this as rho d vi dt is equal to rho for body forces in I direction plus partial derivative of sigma ji with respect to x j direction, which I represent the component of the momentum. So this is in all books. This is the way that you will see the continuity equation. The momentum equation is written. So this is our momentum equation. Now, if we want to write this momentum in x direction, this is this momentum in x direction. This is the momentum equation in x direction. X direction. The momentum equation in y direction will be rho dv in y direction dt. So wherever is I, we put y, rho body forces in y direction plus, and j is represent all the components. So partial derivative of sigma xy with respect to x plus sigma partial derivative of sigma y I state for the main direction with respect to y plus partial derivative of sigma zy with respect to z. So this is the momentum equation in y direction, and the momentum equation in z direction will be rho d velocity in z direction with respect to dt equal to rho multiplied by the body forces in z direction plus partial derivative of sigma x z in x direction plus partial derivative of sigma y z in y direction plus partial derivative of sigma zz in z direction, and this is in z direction. So to simplify, making sure that we are not going to make a mistake, we translated the conservation of momentum statement into a formula for one direction only, and using the end result, we wrote a general form of momentum equation in form of index notation. And now we can easily write the formula for any direction that we want. I hope you liked it. For us to derive this formula in cylindrical and spherical coordinate system, it is going to be a very long process. So what I would do, I will post a video and put the end result. I will write this momentum equation for cylindrical and spherical coordinate system. Again, since we got motion forces involved, we have to do the same thing. We have to write the equation for one direction and then use the index notation form, and then we will be able to write it in all the rest of the components. So I hope you liked it. If there is, I believe after this video I will post these formulas in cylindrical and spherical coordinate system, and then after that I will also write the general formula for the conservation of energy for the system. Thanks.